In this video, I will discuss a JEE Main PYQ from the topics SHM and force on a current carrying conductor in a magnetic field. For some basics, consider a current carrying line element I, dl, and some magnetic field is there. So the force on this current element it's ideal cross B. Now suppose if you have a conductor of finite length L and carrying a current say I, and the magnetic field is uniform and it's perpendicular to the plane of this board, then the force on this thing will be IL B. B is uniform. So dl cross B is dl into B into sine theta. Here theta is the angle between I and this B, which is 90 degrees. I is in this plane of the board and B is perpendicular to the plane of the board. And force is same for all the line elements. The force will add up. So total force becomes ILB. Now suppose this thing is kept on a rail. The magnetic field is uniform. And if it is moving, say with the velocity v, then in this part of the circuit, the flux is changing. So because there will be induced EMF, which is given by Faraday's law of electromagnetic induction as d phi by dt. Flux linking to the circuit is B into A because B is uniform. This will become B into dA by dt. This length is L, and say from here to here, it is Y. So area of this loop is L into Y. So L is also constant, it's not changing with time, so it's come out into dy by dt, which is the velocity of this rod. So once you get the induced EMF, the current due to this induced EMF is this divided by the resistance. This have a resistance R, this conductor. And assume this is a perfect conductor with zero resistance, then the current is VLV by R into L into B. So the force on this current carrying conductor is B square L square V by R. So the force depends on the magnetic field and also the velocity of the rod. So the magnetic field is strong, the force will be strong, and the velocity is more means then the force will also be more. Next basic concept is simple harmonic motion. So there is a mass m here connected to a spring or spring constant k, and there is a fixed support. So there is a relaxed position. From this relaxed position, this is the x direction, this is the origin of x axis. If I displace it and then I leave it, it will start oscillating. Okay, so that is SHM, and the force acting on this mass will be k into x. But now in addition to this spring force, there is one more. I'll surround this thing by a cylinder where is a, say, viscous liquid. So this will oppose a motion of this thing. So it will give a force when it's moving like this, it will provide a force in the opposite direction of the motion, and this damping force is proportional to the velocity. This is the nature of the damping force. In this case, the net force acting on this mass is spring force k into x in the negative x direction, because this is the origin of the x-axis. I'm putting it here and leaving it. So the force due to the spring is towards the negative x direction, and the damping force is BV and also in the negative direction, because When it's moving like this, the damping force will be in this direction. And this is equal to mass into acceleration, net force, that is d square x by dt square. This, if it comes here, b into dx by dt plus k into x equal to 0. So this is a standard differential equation, and the solution of this is, suppose this term was not there, then say SHM. So the solution will be cos omega t plus phi. But because of this term, x as a function of time will be cos omega t plus some initial phase, and this omega will become omega prime, which is different from omega a little bit. And this amplitude will be constant amplitude if this damping term was not there. But because of this damping term, it will be minus b t by 2m. And this omega prime, in the case of this undamped SHM, will be square root of k by m. But see, because of this damping, it will be different from this by a term. So this we have to remember. Once we get this differential equation, the solution of this is of this form. SHM means this amplitude is called, this decay won't be there. But because of this damping, the amplitude is a decaying amplitude. And this omega is from the omega prime, is different from omega of a pure SHM, which is k by m, by this extra term. So with these basic ideas, you can solve this JEE Main question. This is the question. A thin strip 10 centimeter long is on a U-shaped wire of negligible resistance, and it is connected to a spring of spring constant 0.5 Newton per meter. See figure. The assembly is kept in a uniform magnetic field of 0.1 Tesla. If the strip is pulled from its equilibrium position and released, the number of oscillations it performs before the amplitude decreases by a factor of E is N. If the mass of the strip is 50 grams, its resistance 10 ohms, and air drag is negligible, N will be close to. So this is the figure. There is a strip here of length 10 centimeter, uniform magnetic field. It's moving on a rail which is zero resistance. And this thing, if it is pulled from here and released, will start oscillating. It will be in SHM, but because this magnetic field, there will be damping, because magnetic field induce a current in such a direction, it opposes the change according to the Lenz's law. So because of this magnetic force, there will be damping. So it's a damped SHM. Once it's damped SHM, the amplitude will go down with a time constant. So we have to find the time constant, and from that we can get the value of N. You can pause and run this question. So when the strip is displaced here, say by an amount x, then the force is acting on this thing, or the spring will try to pull it back with the force kx, and since it's moving towards right, there will be a damping force in this direction, F into B into V. Okay, so the damping force because of the magnetic force on a current carrying conductor. Is I, L, B, which you already seen. And I can write in terms of the induced EMF d phi by dt, which is B into L into V. So this will become B square L square V by R. So the net force acting on the strip is minus kx and then minus B square L square V by R. Okay, so comparing the standard equation, so this is the value of B. And this amplitude will decay down as A into e raised to the power minus B by 2m into t. So the time constant for the amplitude Rm by a factor of 1 by E is 2m by B. This can be written as where tau is the time constant. So to find this time tau, B is B square, or we can find out here itself, 2 into mass of the rod, 50 grams. So in kilograms, 50 by K, where K is 1000. And then B. So 1 by B is R. Resistance is 10 ohms. And then B square L square. B is 0.1. Length is also 0.1 meter because 10 centimeters is 0.1 meter. So it's 0.1 square and L square. So this is 10 raised to minus 4. This is 1000. So 10 raised to minus 1. So if it goes up, become 10k. 2 into 5 is 10. And then I have 100 here. And then this 1000 is there. So it will become 10. So 10 raised to minus, if it goes up, become 10k. So time constant is 10k seconds. And the time period of this SHM T is 2 pi into square root of m by k. This is for pure SHM. And there will be a correction because of the damped part. Which is actually very small. This is approximately m by k only, because we can calculate that value omega, that b square by 4m square. B square is r, which is 10. So b square is b square l square. So 10 raised to minus 4. B square. So b is just 10 raised to, this is 0.1 square, 0.1 square, 10 raised to minus 4 by r, that's 10. That's this square. B is 10 raised to minus, because this is 0.1 square, 0.1 square, so 10 raised to minus 4 by 10, the whole square, divided by 4 m square. M is 10 grams, 50 grams. So 50 by k whole square. So this is 10 raised to minus 5, 10 raised to minus 10, and then 4 into, this is 50 by k is 50 by 1000. So 20 times. So 1 by 20 square. So this 4 will get cancelled. So it will become 100 square. 10 raised to minus 4. So 10 raised to minus 6. It's small compared to m by k or k by m. K by m value is 0.5 k. M is 50 grams. So 50 by k. So that's into k. So this is 0.1 by 10, so 0.01 into 1000, so it is 10. So k by is 10. So compared to 10, 10 to the minus 6 is very small. So this term can be neglected. So this is approximately square root of m by k. It's a good approximation. So the time period of the SHM oscillation m is 50 grams, so 50 by k, and spring constant is 0.5 SI units. So 5 and 5 will go 10 times. So it become 100 by 1000. K is 1000. Root m is 50 grams. So 50 by k. The spring constant is 0.5. So 5 will go 10 times. And this will become 0.1. So 0.1, 0.1, and then 0.1 into 1000. So it's 1 by root 10 time period. This is approximately 2. So how many this oscillations are there in this 10k seconds? So n will be tau divided by t. This is the time period of one oscillation, and then it starts decaying and keeps on decaying. But this time tau, the amplitude drops down by 1 by e. So in this time tau, how many t's are there? That is the number of oscillations. So tau is 10k by 2, which is 5k, that is 5000. So 4 is the correct option. This is what I explained here. The net force acting on the strip is the spring force minus kx is the negative x direction, and the damping force, because the force on a conductor carrying conductor is ILB, and I in terms of EMF, that will become L square B square V by R. So this form equation can be written as F net is mass acceleration, and this V is x dot dx by dt, and this is B, and then kx equal to 0. So this is standard differential equation. So the solution of this form, cos omega prime t plus phi into this damping term e raised to minus b t by 2m. So the time constant of this damping is minus et by tau, and then tau is 2m by b. So this is a damping term. So in time t equal to tau, this amplitude will decay by 1 by b. So that time you have to find out how much time it takes to decay by a factor of 1 by e. So 2m by b, if you put the b as this one, will become 10k seconds. And the time period of one oscillation is approximately square root of 2 pi into square root of m by k. Put the values for m and k, they will get us 2 seconds. So from this, you get the number of oscillations in the time tau is 10k by 2, which is 5k.